Welcome to the office. We want to continue taking a look at direct products and finitely generated abelian groups, specifically the structure of finitely generated abelian groups. So we've got an abelian group. It might be an infinite group, it might be a finite group. If it's finite group, then it's pretty easy to see that it's finitely generated, but we can have finitely generated groups that are also infinitely large, right? They contain an infinite number of elements themselves. Z, for example, right, is generated by 1. But it, of course, is infinite. So we want to say that each abelian group can be generated by a direct product of cyclic groups. That's what our theorem states. Let's take a look at the theorem here. So every finitely generated abelian group can be expressed as the direct product of cyclic groups. Right, that's really where we're at here. Those cyclic groups are of the form Z sub something. We have a collection of them, and then collections of Z. So if we have a finite group, then it's just going to be this first portion right here. In the case of finite groups, it'll just contain that. In the case of infinite groups, it can contain all of it, or just some of the right-hand side here. Okay, so finite cyclic groups, infinite cyclic groups. So every abelian finitely generated group is isomorphic to something that looks like this. Now, the order of these subscripts, so like prime to a power, prime to a power, prime to a power, so 3 or 9 or 14 or 8, right? Primes to powers there. These can be arranged in any order that we like. That does not necessarily matter. So arrangement doesn't matter. But the things that do matter are how many and precisely which ones of these occur, as well as how many of these copies of Z occur. So the number of copies of Z is called the Betti number. We won't work with that too much. And then again, these primes to a power are unique themselves. That is, if I come up with, right, if I say I have 2 representations, then they're the same representation as, with regards to rearrangement. I can rearrange one into the other every time. I'm not going to get different primes to a power, and I'm not going to get a different number of copies of Z. Okay. So let's take a look at an example of this. 144 is a little large, so we're just going to keep it a little bit smaller at 72 here. We want to find all abelian groups up to isomorphism of order 72. So what we want to notice is that 72 can be written as 2 cubed, that is 8, times 9, which is 3 squared. So we have a finite group, and it's finitely generated. It has to be. And we want to find all groups that are abelian of that order. And this theorem says that we can express it in this way. So you might be inclined to say, oh, well, here's one of them, Z72, that's one of them. But our theorem says that we have to write it in terms of direct products of primes to powers. 72 itself is not a prime to a power, so that's not what we're interested in. However, 72 can be, right, we notice that the distinct primes, we can write 72 as that 8 times 9 here. And this is generated by a single element. So this would be isomorphic to Z72 itself. So Z72 can be written in this way. We're at the direct product of Z sub primes to powers. Fantastic. So we can take this. The book actually builds up, takes all of the individual pieces, 2, 2, 2, 3, 3, and it will put them together until it ends with this. I like to break it down. Whichever approach you take is absolutely fine. So I can split the 9 as 3 times 3. So I'm going to write this as Z8 direct product with Z3 direct product with Z3. So that's the same, prime to power, no issue there. I can write 8 as 2 times 4, so Z2 direct product with Z4. And then I can do Z9 or Z3 direct product Z3 again. So direct product with Z9. And then Z2 direct product with Z4, direct product with Z3, direct product with Z3. So the 8 and 8 can get paired with 9, 3, 3. 8 can be broken up as 2 times 4, which can again be paired with 9 or 3 times 3. And now I can break the 4 apart. So I have Z2, direct product with Z2, direct product with Z2. Right? I broke up the 4 now. And I have Z9, and I can break the 9 apart. Z2, direct product with Z2, direct product with Z2, direct product with Z3, direct product with Z3. So there are 6 different groups that are abelian, of course, of order 72 up to isomorphism. Again, we use that phrase up to isomorphism to mean that, yeah, I could have, I could have a group and call it something different, but it's going to be isomorphic to one of these things. So these are my only distinct groups of order 72. These are not isomorphic to one another. I might have other groups that are isomorphic to this, on the other hand. All right, that's all that I wanted to share for this example. So thank you for your time and attention. Have a great day.